Good afternoon. So this is Advanced Thermodynamics and Combustion by IIT Guwahati under the NPTEL program, and we are into the sixth live tutorial session of this course. And the theme of today's this session's discussion will be properties of gas mixture. So, also the instructor of the course is Professor Niranjan Sahu from Department of Mechanical Engineering, again IIT Guwahati, and I am Aditya Sharma, your teaching assistant for these sessions. So we shall start in another 5 minutes. Okay, thank you. Okay, so we can start with the session. So, as I said, the theme of today's uh, question and discussion will be on properties of gas mixture. So, basically, in this week's lectures, what has been discussed is when we are dealing with mixtures, right? So, in that case, if we have to get different properties related to mixture, right? Because eventually the whole idea is to thermodynamically, in terms of thermodynamics, we want to study our system, right? So in this week, in that context, we are dealing with mixtures, right? So two lectures are there. So in these lectures, first we have real models, real gas models, and ideal gas models, right? And then after that, we move on to the mixtures. So different properties related to mixtures, how we define all these properties, and what are the importances of these properties. So all this has been covered in this week's content. Okay. So we will perform this session as we have been doing previously. So, firstly, the first section will have topics, okay, and then we will discuss conceptual questions. After that, we will take numerical questions. Okay, so let's start with the session. Okay, so these are the topics in your lecture 15 content. Okay. So the first heading here we have pure substances and phases. So this topic majorly we have covered in previous lectures. So here it has again been revised that what are pure substances and phases, right? And then in very detail we discussed phase diagrams in previous lectures. So these phase diagrams again have been discussed here, right? So phase diagrams like pressure versus temperature diagram, right? So maybe I can quickly draw this. This is your pressure and this is your temperature. So this was your triple point. Then this is your solid region. This is your liquid region, and this is your gas region. Okay. And then these three lines correspond to different curves. So this is fusion curve. This is your vaporization curve. And this is your sublimation. So this is your phase diagram. Okay. After that, and please feel free to ask or interrupt me if you have some doubt. Okay, I'll try my best to answer your questions. Right. So next we have pressure. Okay, pressure volume diagram. So pressure volume diagram, just for revision, I'll quickly draw it. I hope my mic is on. Yes. So, so this was your PV diagram, right? Right. So different isotherms have been drawn. So I'll just draw this vapor dome, right? So inside this vapor dome, two phases can coexist. Okay. So then there are isotherms like these. One will pass through this point, right? Which is your critical point. Then this is your liquid vapor phase coexisting, right? Okay. And these are isotherms, which means they have same temperature, just specific volume and your pressure is changing here. Okay. Okay. Right. Then then you have next diagram is temperature volume diagram. So in temperature volume diagram, like in PV diagram, we have isotherms. In temperature volume diagram, we will have isobars. The different lines here correspond to constant temperature, constant pressure. Sorry, this is your temperature and this is your specific volume. So something like this, right? And this is your critical point. Okay, and these are isobars. That is, pressure in these lines will remain same, right? Now, so this is your temperature volume diagram, right? And like it was in this PV diagram, here also inside the dome, two phases coexist. Okay, right. Then next topic is equation of state. So the idea of equation of state is to have a mathematical formulation by means of which we can define our state. Right? So in it first we saw that a PV and P, these two terms have been related. I'll just write this down. PV and P. These a equation has been shown, right? Where these two have been related by means of a mathematical equation, right? So this defines your equation of state for a particular gas you are studying, right? Okay. And then moving on to compressibility chart. So compressibility chart basically is chart of Z versus your reduced pressure, right? Now, what is Z and what is reduced pressure? That we should see. So compressibility chart. So your compressibility chart has Z and PR, right? So now what is Z? So Z basically is compressibility factor. Okay. And it is given by please remember that whatever discussion or terms or equations we introduce, all this is from the perspective that we want to know our system better, right? And then using that information, we want to analyze our system. So the basic idea remains this, right? So this you should never lose this point, right? And in this context only, you should try to visualize all the discussions. Okay. So this is your compressibility factor, right? And for a limiting case, so when pressure is very low, okay, in that case, this has a limiting value of 1. Right? So this you need to remember. Okay. And then what is PR? And PR is basically your pressure divided by your critical pressure. Okay. So with reference to your critical pressure, the pressure of the gas that we have, so this ratio is reduced pressure, right? And similarly, we define reduced temperature also, which is nothing but temperature of your gas or mixture to critical temperature of that gas. And using these reduced pressure and temperature, we can then find out reduced specific volume, which is if this is your specific volume of gas. So this will be your reduced specific volume, which we in this case call pseudo reduced specific volume. Right. So this is about your compressibility chart. Okay. Then moving on to real gas models. So in this topic, two real gas models have been discussed. One is your van der Waals equation. Then second one is Redlich-Kwong equation. Okay. So through these two models, we relate pressure, temperature, and specific volume for real gases. Okay. So your van der Waal equation is this. And then your Redlich-Kwong equation is this. So these are the two real gas models that have been discussed, right? R bar is your universal gas constant, T is your temperature, right? This V bar is your specific volume. Then A and B are your constants. Okay. Right. Then next is your ideal gas model. So ideal gas model, very widely discussed, right, and used. So we are well aware with what is ideal gas model. Right. This is PV equals to nRT. Okay. So after your ideal gas model, so this is about your lecture 15. And then in lecture 16, what we saw is gas mixtures or solutions. Okay. So the idea is that when we are doing some thermodynamic analysis, so if we have two gases that comes into contact, right, they mix with each other. In that case, how we define that thermodynamically, right? So that happens a lot, right, in your thermodynamic studies. So if you take combustion, right, or any other thermodynamic case, in that case you will have to deal with such mixtures, and to study them thermodynamic analysis. So this discussion has been brought into picture. Okay. So in this lecture, First is your basic relations of gas mixture. Okay. So in this, you have mole fraction defined, and then number of moles, right? And then if you have to use your real gas model, some of the real gas models, in that case, if you have to define the constants, so you define your constant based on the mole fraction of different components of that mixture. So here I'm dealing with discussing a mixture and not a single entity, right? Not a single component system, but multi-component system. Okay. So mole fraction we know, right? So this was your lecture 15, and then this is mole fraction. So if we have some component I, right? In that case, its mole fraction will be number of moles of that component and then total number of total moles in a mixture. Number of moles of component I. Okay. So this is your mole fraction, and number of moles is simple. Just you have to add, right? Total number of moles in a mixture. Okay. Then so mixture equation of state is, I was discussing that, let's say if you have so like in the lectures it has been discussed. So if you have a Radlick-Kwong equation, right? Then to define it for a mixture, you'll have to define its A and B. And how you define A and B is, so this you can also write as Yi, mole fraction. Okay, mole fraction you can write as Yi. So in that case, for example, you have to define A, right? In Radlick-Kwong equation. So you define it with the help of your mole fraction. So Yi is the mole fraction for your component I, right? So this is for your Radlick-Kwong equation, right? For a mixture. When we introduced it in as a real gas model, in that case, we meant only a single gas. Okay, but when we are discussing it here, we mean a mixture. It can be two components, two component system, three component system, four component system, right? Three, four gases mixing together, all this. So in that case, we define it this way. Okay. Then is your case rule, then additive rule. Okay. So this is your case rule, right? So case rule basically is to obtain your critical entities, right? Properties at critical point for a mixture. So this is basically case rule. So for a mixture, if you have to define your critical temperature, you define it this way, where J is the total number of components. Okay. Then similarly, where TCI is the critical temperature for your component I, right, in its single state. So if you have the ith component in its single state and not as a mixture, in that case, what is its critical temperature? So TCI is that temperature. Okay. So similarly, critical pressure can be defined. Okay. So this is it. So this is your case rule. Then moving on to your next topic, and I hope I am audible. If not, please inform me. Otherwise, let's continue. So then we have our additive rule. So what is your additive rule? So additive rule basically says that the different components we have in a mixture or a solution. So if we want to define the some property of that mixture, okay, so we can directly add the individual value of that property of a particular component. So we can all add such individual values of different components to get your our total value for the mixture, right? So this is your additive rule basically, right? So using the additive rule, if you want to find pressure, so simply of different components, the pressure we have, we can do this. But this is done at some particular temperature and volume, right? And similarly, volume, if we are defining your using additive rule, So this is done at some particular temperature and pressure. Okay. So this is your additive rule. Now is your multi-component system. So multi-component system basically is when we have more than two or more than components in a system, right? And then to define these uh, systems or mixtures or solutions, three parameters we have introduced, right? One is partial molar property, second is chemical potential, third is your fugacity, right? Please remember all of this we are doing just for our thermodynamic analysis. Okay. So if you keep the bigger picture in mind, so things remain a bit sorted. Okay. So let's say we have some property X. Okay. Let's say we have some component. Okay. In a mixture. So maybe let's say it has two components, right? Component one and component two. So out of this, we have a property x1 of component 1 and the same property x2 of component 2. Okay. So in that case, if we want to define the partial molar property, so partial molar property basically is defined this way. So we denote it with the bar. Okay. So this is your partial molar property. Okay. So this basically is partial differentiation with respect to the number of moles that are there in this particular component, that is component 1 in the mixture, the number of moles that are there of component 1. Okay. Right. So this is a partial molar property, and then there is chemical potential. Now, what is chemical potential? Chemical potential is nothing but your molar Gibbs function, right? Chemical potential is your partial molar Gibbs function. Okay, so which we define also by mu. So this is G by, so let's say it is for some component I, ppni, right? So this weight should be n1. Okay, so this is your chemical potential, right? So if we have some component in a mixture and we have the Gibbs function for this component, in that case, the chemical potential that this component holds, or the share of chemical potential that this component holds, is defined using this. Okay, so this is nothing but partial molar Gibbs function. This is your chemical potential. Okay, then what is fugacity? So fugacity is something like pressure. Okay, it has units of pressure, right? And we define fugacity as this. So your C bracket T is some constant, okay, and F is your fugacity. Yes. Right. Okay. Right. And one mathematical property related to fugacity is that at small pressures that are tending to zero, this ratio becomes 1. So maybe if this is of some use in future, so we can use it. So this is your fugacity. Okay. Then next topic is your ideal solution. So in this discussion, basically the crux is that there is, so if we see our solution, right, in terms of volume, right? So if you see your lectures content, so in slide 18 of lecture 16, it says that there is no change in volume on mixing pure component to form an ideal solution which follows additive rule. For an ideal solution, here these two terms remain same. Okay. Yes. So this is your molar specific volume, and this is your partial molar specific volume. Okay. So in case the solution is not ideal, so these two are not different. And after we get a mixture, there is a difference between these two. But for ideal solution, there is no difference. Okay. So this is your ideal solution. So now moving on to questions. So this is your first question. Which is based on phase diagram, and it states that a state at which the phase change begins or ends is called as saturation state. So whether this is a correct statement or not. Yes, we can try to answer this. So we can look at this diagram. Okay, so this is phase diagram. In it, if you see, we have three curves, right? So first is your fusion curve, then is your vaporization, right? So your question says that when your question says that a state at which the phase change begins or ends is called as saturation state. So in that case, it means that these lines, right? So these lines, because across these lines, phase change is taking place. So it means if the statement is correct, so these lines should be your saturation line, right? So which is also the case, right? When your some single phase saturates, right, and starts switching to some other phase, in that case we call it a saturation state. So this statement is correct in that sense. Okay. So this is your question number one. So next question is on phase diagram again. And the question says that each saturation pressure has a number of saturation temperatures. So pertaining to a saturation pressure, so if in a single phase some matter has is in a saturation state. So let's say in that saturation state it has some pressure. So pertaining to that saturation pressure, is it possible that it can have a number of saturation temperatures? So this is what the statement asks from us. So we can try to answer this. So the point is that when we have some matter in a saturated state, in that case, for a particular saturation pressure, it will only have a single saturation temperature pertaining to that saturation temperature. Okay. So when the statement says that it has a number of saturation temperatures, that is not a correct statement. In that case, it becomes a false statement. So if you see the answer of this question, so it's B. It's a false statement. Okay. So moving on to next question then. So these questions are from your lecture 15. So next question is on phase diagram. Please read the question and try to answer this. Okay, no answer. So I'll just then read out. So this is again on phase diagram, and the question says that the line representing the two-phase solid liquid region on the phase diagram slopes to the right for substances that it should have been expand and not expands on freezing, and to the left it slopes to the left for substances that contract on freezing. So first is your phase diagram, then is solid liquid region, then the question talks about sloping. So one is the case when on freezing the substance expands, and one is when the freezing takes place and the substance contracts. So this is your phase diagram, and this is your fusion curve. Basically is the solid liquid region, right? So in case there is freezing, right? That is, temperature will decrease. And if you see the current curve that I have drawn, so this is basically sloping to the left, right? So this basically is sloping to the left. So this means that if your temperature is decreasing and your pressure is increasing, so that is sloping to the left. So that is basically the case for expanding, right? But the statement has written it in opposite way, right? And if your curve is sloping towards right, in that case, if temperature is decreasing, it means pressure is also decreasing, right? And it is contracting. So this basically should have been left and this should have been right. So in that case, this becomes a false statement, okay? Okay. So next question is this, but before that, because it's already 4 p.m., right? So we'll have a 5 minutes break and then we will continue with the remaining session. Okay, thank you. Okay, we can start with the session. So the next question is question number 4. This is on pressure volume diagram. And this says that for a single phase of a PV plane at a fixed temperature, the pressure decreases continuously as the pressure volume increases. So if the pressure is decreasing, then pressure specific volume is increasing. So let's see our PV diagram. So this is our PV diagram. Okay. So for a constant, because the question says that at a fixed temperature. So in PV diagram, we know that we have our curves as isotherms. So that means that the temperature remains same along a single curve. So the pressure decreases and the specific volume increases. So if you move from left to right on any curve, so you can see that pressure will decrease. And in that case, if you see the specific volume, so it is increasing, right? So the statement that is given to us says the same, right? Pressure decreases continuously and the specific volume increases. So this is a true statement. Okay. Yes. So moving on to next question. Please read the question and try to answer this. Yes, no answer. Okay. So this is question number 5, and it is on temperature volume diagram, and it says that in a single phase region at fixed pressure, the temperature increases continuously when the specific volume decreases. So temperature is increasing and the specific volume is decreasing. So let's see the temperature volume diagram. So this is your temperature volume diagram. In it, the curves that we see, so along a single curve, the pressure remains same. So this is an isobar. Okay. Okay. So at a fixed temperature. So that means along an isobar, the temperature increases and specific volume decreases. So if you see the graph to or diagram, the temperature if increasing, then specific volume is also increasing. So there is a direct relation, right? In a single phase region, right? In that case, this becomes a false statement. Okay. So for a TV diagram with there's a direct relation between temperature and specific volume in a single phase region. Now the next question is based on equation of state. And it says that the ratio of pressure of gas to the triple point pressure approaches dash as both pressure and triple point pressure approaches to zero. So as the pressure of gas and the triple point gas temperature decrease continuously and reach to a level where they are approaching zero. In that case, the ratio, this ratio P by PTP, so what will be its value? So this is what the question asks, and the four options we have are 0, 1, infinite, to value independent of the nature of gas. Yes. What is the answer to this question? So this is the case. So this is a limiting case, okay? Because if both the pressures are approaching to zero, in that case, what happens is this ratio becomes independent of the nature of gas. Earlier, this ratio would have depended on the nature of the gas, but as the pressures decrease, in that case, this ratio becomes independent of the nature of gas. Directly, its value, right, is correctly not have been mentioned in one of the options, but yes, D option is a correct statement regarding this fill in the blank. Okay, statement question. So D option is correct in this case. Then next question. Question number 7, which is on compressibility chart. So this asks about the units for a universal gas constant. Which of the following is a correct unit of universal gas constant? So this can be solved how? This can be solved from here. So this is your question number 7. So if you see your ideal gas equation, this is nRT. So R is PV by NT. Okay. So PV has units of energy. Okay. N is for your mole, T is for your Kelvin, right? So if you see your question, energy has been mentioned in terms of joules, kilojoules, and moles have been mentioned in terms of kilomoles, K mol, and temperature has been mentioned in terms of Kelvin K. So here this becomes kilojoules per kilomole, then Kelvin, right? So, or maybe this is correct or not, I'm not sure this particular sign, but yes, from here to here falls our question. Okay, so this is kilojoule per kilomole Kelvin. So out of these options, C option is the correct one. Right? So then we'll move on to next question, which is question number 8. So please read the question and try to answer this. The question is on compressibility chart topic. So this is question number 8, and it states that at states of gas where pressure is small relative to critical pressure, Z, the compressibility factor is approximately equal to dash. So out of these 4 options, which one is correct? So question talks about compressibility factor. So this is your compressibility factor, PV by RT. So when the pressure of gas is very small in comparison to the critical pressure, in that case, what happens to the compressibility factor? So in that case, this compressibility factor becomes 1. Okay, please remember. Okay, so this was your eighth question. Moving on to ninth question. So this is based on real gas models. And this states that, so it has given few statements and it asks which of the following is, so which of the following statements was introduced as a concept in van der Waals model. So in when we saw van der Waals model in lecture 15, so two different concepts were introduced while defining this model. So out of the given four options, we have to tell that which one is out of those two in the given four options. So the first statement is the real gas molecules occupy less volume with respect to ideal gas model. The real gas molecules occupy more volume with respect to ideal gas model. Then third C option is due to repulsive forces between the real gas molecules. They exert less force on the container in comparison with ideal gases. And the D option is due to attractive forces between the real gas molecules. They exert more force on the container in comparison with ideal gases. Yes. So what will be the answer to this question? No answer in that case. I'll discuss this. So your first concept that was introduced in the van der Waals model was that the real gas molecules occupy more volume in comparison to ideal gas model. So on the volume, there are two options. That is option A and B. So one says that it occupies less volume and the second one says that it occupies more volume. So the more volume option is correct. Then second concept was based on the attractive forces, right? And it says that the pressure that the real gases exert on the walls of a container in which they are is less in comparison to the ideal gas models because there are attractive forces also between the molecules. Okay, which result in less pressure on the walls of the container in which they are. Okay, so C option says that due to repulsive forces between the real gas molecules, they exert less force. They do exert less force, but the reason for that is not repulsive forces. Okay, so not a this is not a correct statement. And then the fourth option is due to attractive forces between the real gas molecules, they exert more force on the container. Due to attractive forces between the molecules, they exert less force. Okay. So in that case, it should have been less here. In that case, this also becomes a wrong statement. Okay. So only option B is correct. Okay. So this is your question number 9 on real gas models. The next question number 10 on multi-component systems. It says that the partial molar Gibbs function for an arbitrary component in a mixture is termed as the fugacity of that component. So whether this statement is true or not, this is basically a definition type of question. So if you know the definition, you know the answer. So what is fugacity and whether the statement is correct in terms of fugacity? So partial molar Gibbs function basically is this. If I is the component number, this. So we have seen that this is what your chemical potential. Partial molar Gibbs function is also called as chemical potential. Okay, and not fugacity. So this becomes a false statement in that case. Then moving on to next question. So it says, it asks that whether chemical potential is an extensive property or intensive property. So we know that an extensive property means that a property which depends on the quantity of the matter, okay, which we are dealing with, and intensive property does not depend on the quantity. For example, is an intensive property or mass. They are extensive properties. So whether chemical potential is an extensive property. Chemical potential, that is a partial molar Gibbs function, okay, is an intensive property. So it doesn't depend on the extent of your matter, but is just an intensive property. So when the question asks that whether, when the question has given that it is an extensive property, in that case, this becomes a false statement. Now, next question is, Lewis Randall rule is related to which of the following topics? Yes, please. So what is a Lewis Randall rule? Question number 12, this is. So Lewis Randall rule says that if you want to find the fugacity of the whole solution, okay, so we can do it by using this expression. So ideal solutions, this is the Lewis Randall rule. So for ideal solutions, it holds good. So this basically is if you have n number of components in a mixture, you take one component, you take its mole fraction, multiply the fugacity of that component in its pure form, right? With its mole fraction, you get a product, and for each component, you do the same thing, and you just add up all these multiplications that numbers for different components you get, right? And eventually you get this fugacity of the component in ideal solution. Okay. Sorry, I made a mistake. So this is basically the only fugacity if we have different n number of components, and then we have a mixture of these components in a mixture. So let's say we have component number one. It has some fugacity in its pure state. The, just give me a second. I just got disconnected from my. Okay, we are good. So I was talking about fugacity. So in its pure form, if component number one has fugacity Fi, in that case, when this component is in a mixture form, the fugacity of this component in the mixture, that is Fi bar, will be equal to its mole fraction and then its fugacity in its pure form. So this is your Lewis-Randall rule. Okay. And your question says that Lewis-Randall rule is related to which of the following topics? So this is related to fugacity only. Okay. So moving on to now question number 13. So this question is on ideal solution. So please read this question and try to answer this. Okay, so no answer. So the question is the partial molar volume of each component in an ideal solution is equal to the molar specific volume of corresponding pure component at the same temperature and pressure. So one is partial molar volume in the that we define when we have a component in a mixture form. In some mixture, if we have some component, let's say x1, so its partial molar volume has been mentioned, and then its molar specific volume in its pure form has been mentioned, right? So partial molar volume is your VI, and then your this molar specific volume in its when it is in its pure state and has not mixed with some other components. So these two things are there. So when we have a ideal solution, in that case you have same values. Okay, so this is and this holds true for your enthalpy also. Okay, same partial molar enthalpy and then molar enthalpy. These two will be same for an ideal solution. And same holds good for your internal energy also. The partial molar internal energy for a component in an ideal solution will be equal to its molar internal energy in its pure form at the same temperature and pressure. Okay. So this is a correct statement. Okay, option A is correct in that case. Now the last conceptual question of this session. After that, we'll do two numerical questions. So this is question number 14. It says that the sum of mole fraction of mole fractions of all components in a mixture is. So this is a piece of cake is 1 equal to unity. So we are done with the conceptual questions for this session. Now we will move on to the numerical questions. So this is our first question and we'll solve this. Temperature of should have been small. So temperature of neon, which has molecular weight of 20.2 kg per kilomole, is being increased from 310 Kelvin to 445 Kelvin in a constant pressure heating process. Pressure remains constant in this process. Calculate the rise in the specific enthalpy. So gas is behaving ideally we have to tell that what is the change in specific enthalpy that this process, because of this process, the gas has encountered. Okay, so let's solve this. Enthalpy we can write as this. Now for neon, because it has 3 degrees of freedom, right? Its Cp by Cv value is 1.66. So its Cp can be written as this, and Cv, if I'm not wrong, can be written as this. So we are concerned with Cp only. This is its R value. R bar is the universal gas constant. M is 20.2 for neon, and your R comes out to be 0.4115 in SI units. Okay. Then Cp is pi by 2 R equals to 2.5 into 0.4115, which comes out to be 1.0287. So this is your specific heat at constant pressure. Then delta H becomes, so this is your kilojoule per kg Kelvin. So 87 into 445 minus 310. So this becomes 138.87 kilojoule per kg. Let's confirm the calculation again. Okay. So this seems to be correct. Okay. So now we are left with the last question of the session, which is as follows. So please try to solve this. So this basically is your question. So we have an oxygen tank with a capacity of 3.24 meter cube, and it holds 7 kgs of oxygen, and then molecular weight of oxygen we know, and the temperature at which this holds this oxygen is 332 Kelvin, we need to determine the pressure in bar inside the tank. So this has to be done using van der Waals equation. Okay. So question number 16, solution. Pressure as per van der Waals equation is given as V square. This is your R bar. Now we will find out the volume occupied by 1 kilomole of oxygen, right? So 7 kgs is occupying 3.24. Okay, so 1 will occupy 3.24 by 7, and 32 kgs, that is 1 kilomole, will occupy 3.24 by 7 into 32. So this comes out to be 14.81. Okay, so this is the volume being occupied by oxygen. So placing this in this van der Waals equation, so this comes out to be 1, which is nothing but this is in pascals, 861 bar. Okay, so this is your answer, and we are done with today's session. Okay, so I'll quickly conclude the session. So this was tutorial number 6 of advanced thermodynamics and combustion. So the theme of this session was properties of gas mixture, where we saw real gas models, ideal gas model, and then we saw properties related to gas mixtures, right? Properties like fugacity, chemical potential, right? And at the end, and also we saw various rules that govern the properties of these mixtures. And at the end, we also saw a special case of ideal solution. So how different properties behave in that case, we saw that. And after that, we moved on to conceptual questions, where we discussed 14 conceptual questions based on the content of week 6. And after that, we did two numericals also based on real gas model and ideal gas model, right? So this was it for session number 6. And we shall again meet for the next session in the coming Sunday with the same timing, that is 3 to 5 p.m. Till then, I'll say thank you for joining the session, right? And keep learning. And goodbye till the next session. Thank you.